All right, aloha and welcome to my talk on making and breaking Mac firewalls. My name is Patrick Wardle. I have worked at a variety of acronym places. Currently, I am the Chief Research Officer at Digita Security. And very briefly, at Digita Security, we are working to create cybersecurity tools for the Mac enterprise. I'm also the creator of the Mac security website and tool suite Objective-C. Okay, so today we're going to be talking about first creating and then breaking firewalls on macOS. Now, in terms of creating firewalls, we'll look at how to make a kernel-level socket filter firewall. Then for the second half of this talk, we'll put on our hacker hats, this will be white, black, or gray, and we'll talk about bugs and bypasses in all third-party Mac products. Okay, so imagine you decide, hey, I want to write a firewall for macOS. In this section of the talk, we will articulate or describe exactly how you would go about doing this. Now, there are many reasons you might want to create a firewall for macOS. Today we're going to be more focusing on firewalls as a cybersecurity protection mechanism versus, say, a privacy mechanism. So our goal, therefore, then, is to be able to monitor all network traffic. And with the ability to monitor all network traffic, we want to be able to allow traffic that is trusted or legitimate, for example, system-level protocols and processes. And then for any traffic that is unauthorized, something perhaps we don't recognize, or traffic that is from a malicious process, we want to obviously block that. And then armed with this capability, that is being able to monitor all traffic, we should be able to, in theory, detect generically most infections. So imagine an attacker has somehow gained code execution on your Mac system. Perhaps they even have a zero-day for the browser. And they've then been able to persistently install something on your system. When that persistent backdoor implant wakes up and tries to connect to its command and control server for tasking, or perhaps tries to exfiltrate data, this will obviously generate network traffic. And if you have a firewall installed on your system that's monitoring all traffic, it will be able to generically detect that this is new, untrusted traffic, and will thus alert you that something's going on. So very easy to see that these firewalls are actually a very powerful protection mechanism that can generically detect and cover even brand new malware threats. Now, since we want to be able to monitor all traffic globally, we're going to have to write a kernel extension or a KEXT. In macOS, Apple provides something called Network Kernel Extensions, or NKEs, and they provide a way to extend or modify the network infrastructure in the kernel. And one type of NKE is a socket filter, and which, as its name implies, allows you to filter network traffic at the socket level, which, for a firewall, is exactly what we want. Now, in order to filter network traffic via a socket filter, we'll describe the steps taken to accomplish that. And the first thing you have to do is register your socket filter with the OS. Now, there's this great book called OS X and iOS Kernel Programming, and it describes many ways or many types of activities you want to do in the kernel, and one of them is a brief chapter on creating a kernel-level firewall. So as I described in the book, the first thing you should do when registering a socket filter kernel extension is to fill out something called a socket filter structure. We have the definition for this structure on the slide. We can see that this structure has various callbacks, and when you populate these callbacks and register the structure, anytime a socket operation occurs, your callbacks will be invoked, allowing you, of course, to examine the operation. So, for example, when a new socket is created, when data is sent or received, again, the operating system will invoke your callbacks. So once you've populated this socket filter, you invoke the sflt_register function, and this will register or install your socket filter kernel extension. Now, besides that populated socket filter structure that we just talked about, this function also takes the socket domain type and protocol. So this means if you want to monitor various socket types, you have to invoke this function multiple times. So for example, if you want to monitor TCP and UDP, you have to call this function twice for that. And also if you want to, for example, monitor both IPv4 and IPv6 traffic, you have to invoke this function for each of those socket domain type and protocol groups. All right, so now let's talk briefly about those callbacks, which, as I noted, the operating system will invoke anytime a socket operation occurs. First, we have the attach function. And as we can see on the slide, as the statement says, this will be automatically invoked anytime a new socket is being created. And it's called with the socket and then also a cookie parameter that's designed to hold per socket data. So you can store anything you want. It's basically just a parameter for your firewall or for your callback to store perhaps some information about the socket. So what we do is we allocate a chunk of memory and we store an action based on the PID of the process if we've seen that process before. So if it's a trusted system process, perhaps the DNS daemon or some software update component of the operating system, we will set this to allow. If it's also something that the user has indicated should be allowed, for example, their browser or a chat application which is authorized to access the network, similarly we set the action in this cookie parameter to be allowed as well. Now if it's something the user has said to block, perhaps it's some Adobe process that they don't want talking to the internet or some other third-party app that they don't want talking to the developer's cloud, we will set the action to block. And finally, if it's a new process, if it's something we've never seen before, we will set the action flag to ask. All right, next we have the connect out callback, which is invoked by the operating system when a socket attempts to connect out and send data. This function takes that same cookie parameter, which we have set an action with, and in this action, we can see if we've decided to allow, block, or to ask the user. So if the action has been sent to allow, this means this network connection is authorized or should be allowed, we just return an OK status from this function, which tells the operating system that yes, we are OK allowing this network connection to proceed. Now, if this is a socket connection we want to block, we return an error code from this function, and this tells the operating system that this network connection should not be allowed, and since we are returning an error, the operating system will drop or block that connection. And again, if it's a new or unknown process, we're going to have to do some extra logic to basically ask the user in user mode what they would like to do. So if we don't recognize the PID, if it's a new process, as I mentioned, we have to ask the user to figure out what action to take. So in the kernel, we put the thread to sleep, and then we ask a user mode daemon to handle this request. And we do this by pushing information about the connection to a shared queue. Specifically, we pass the PID, the socket, and the address it's trying to connect to. So the daemon is listening on this shared queue. It gets this request from the kernel extension from kernel mode, basically saying, hey, I have a connection, I'm not sure what to do about it, please help me decide what to do. So the first thing the daemon does is it maps the PID to a process path and checks if the process path exists in its rule database. For example, this might be an application that has been pre-authorized, but it's just the first time it's run. If it's found, it responds with the action back to the kernel. However, if it's a path of an application that the daemon has never seen before, it's going to have to ask the user. So what it does is it sends an XPC message to an instance of the firewall that's running in the user's UI session, which will then display an alert to the user, asking the user what they would like to do. The user's response, which will be allow or block, is then passed back to the daemon. The daemon will update its rules database to save the user's response. And then it will respond back to the kernel extension via an IO-kit interface. The kernel will then get this message. It will wake up the thread that it had put to sleep that was attempting to perform the network connection and will apply the user's response. If the user said allow, it will just return OK, which tells the operating system to allow the network connection. Otherwise, if the user has said block, it returns an error message from the callback, which tells the operating system to block and drop the connection. So let's briefly take a closer look at identifying or classifying processes. So recall that the kernel extension has intercepted a socket operation, for example, a new socket that's trying to connect out to some server. And specifically when the operating system invokes this callback, it will call this callback will occur in the process context of the process that's trying to create the socket operation. So if it's a browser, the callback will occur in kernel mode, but in the process context of the browser process. This means we can call the proc_self PID function, which will give us the actual PID of the process. So as I noted, we pass this to user mode. The kernel will the launch daemon will map this to a path, and then it will also generate the code signing information for this process. Because in the rules database, what it stores is a path to a process, an action, that is, if it's allowed or should be denied, and then also the code signing information about this process. This is to prevent malicious subversion of trusted applications. So for example, say the user has trusted their chat application. If a malicious piece of code tries to modify the chat application, when the daemon recomputes the code signing information, it will detect there's been a malicious modification and thus not blindly allow the application. The other feature that a firewall has is that for any network event that occurs in kernel mode, it will broadcast this to user mode via a system socket. And it does this to allow third-party code or any user mode code to subscribe to these events. So what it does is it broadcasts the PID, the socket, and the address that the socket is trying to connect to. So say you want to write a network monitor. What you can do now is very easily just connect to this system socket and read off it. And as network events happen in the kernel, these will be detected and broadcasted to them. So we can see in a few lines of code on the slide, you basically connect to that instance of the system socket and then read off the socket. So again, very easy, for example, to build a network monitor, or perhaps if you have your own or a third-party monitoring system that's running in user mode, or you just want to log a network activity, very easily you can do that by means of our kernel interface. All right, so if we put all of this together, we have Lulu. So Lulu is a free firewall. I am a passionate believer that for end user security products, we should not be making our users pay for these. And also the full source code for this entire firewall product is online. Again, I'm a huge fan, especially for security tools, that the full source code is available, both for auditing reasons or just to see what's going on. Right? If you're installing someone's kernel extension, I would hope that they're making the source code available for that. Otherwise, that's asking for a very high level of trust. Okay, so this conference is primarily a hacker conference. So let's kind of turn our attention to the other point of view and talk about how we can break such firewalls. So our goal is simple. Again, we've put on our hacker hats. Maybe you're a pen tester, maybe you're a government employee doing offensive cyber operations, or perhaps you're even a cyber criminal. Hopefully not. But assume you've gained access to a Mac system that has the firewall installed. Obviously, what you want to be able to do is install some backdoor or execute some commands that will likely generate network traffic. Maybe exfiltrating some user data, perhaps connecting to a command and control server for tasking. Unfortunately, if there is a firewall installed, it will detect this activity and alert the user. So again, we want to figure out ways we can access the network in a way that will not be detected by the firewall, or at least won't generate an alert to the user. So in this section, we'll first look at some existing firewall-aware malware. We'll then talk about some exploitable issues in security products, in firewalls. And then we'll talk about how to bypass these products altogether. So as I mentioned, it's very important for an attacker or piece of malware to detect that a firewall is installed. Otherwise, it really might be their undoing, as the firewall might be the piece of software that ultimately catches the fact. And as you can see on the slide, this really does happen. There was a red team scenario against Palantir. The red team was wildly successful right up until a firewall detected their activity. And as we'll see in the rest of this talk, there's really no excuse for this. These products are fairly easy to bypass, but you have to be aware that they're there. So it turns out there's some existing malware that is firewall aware. But what I mean by that is that they will actually look for the presence of a firewall to see if it's installed. Now, I've yet to see any public Mac malware that will then try to actively bypass these firewalls, but that's something we'll likely see in the near future. However, what this malware does is look for these firewall products, and if it detects them, it basically says, okay, I know this firewall product would alert the user if I continued with my persistent installation and connecting, for example, to my command and control server for tasking. So I'm actually going to abort and not infect this system if there is a firewall product installed. So the first example of this is Devil Robber. And what Devil Robber did was it infected users via a Trojanized instance of the Twitterific application. And if we look at the install script for this Trojan, for this backdoor, we can see that it's looking for the presence of Little Snitch, which is the most common third-party Mac firewall product. And if the malicious install script finds the Little Snitch kernel extension, meaning that there's a firewall installed on the system, we can see the malware will do two things. First, it executes the benign, uninfected instance of the application so that the user doesn't see anything amiss, but then it will exit. So again, the attacker, the malware author, has decided to basically give up on any boxes that have a firewall installed. Another more recent piece of Mac malware that utilizes a similar technique is OS X Proton. If we reverse engineer the malware, we can find an encrypted configuration file. If we decrypt this config file in memory, we see strings, or specifically paths, to the three most popular third-party Mac firewall products: Little Snitch, Hands Off, and Radio Silence. If we look then at the disassembly for the malware, we can see that for each of these kernel extensions, it's checking if they exist on the file system. And again, if Proton finds that any of these firewall products are installed, it actually just aborts and doesn't persistently infect the system. So again, the malware author was willing to give up infecting certain systems versus risking detection. All right, now on to some real issues. So firewalls, as we've discussed, are rather complex pieces of software. And in order for them to gain insight and control all network traffic, they have to have a kernel component. Now, unfortunately, especially these third-party firewall products, they're often not as written securely as the operating system, nor have they been as well audited. So if you're a local attacker and you're looking for local privilege exploits or elevation of privileges, such firewall products are a great place to start. So a few years ago, I was taking a quick look at the Little Snitch kernel extension, and I found which turned out to be a rather neat bug. So the Little Snitch kernel extension was taking some data from user mode, and specifically it took a 64-bit value. And it used that in both a allocation and a copy routine. So if you look at the code, you see, okay, they take this value and they allocate and then copy. And it's like, okay, that looks okay, right? They're using the same value. The problem was the allocation routine that they use, which is a macOS allocation routine, expects a 32-bit value. So if you pass it a 64-bit value, it will actually truncate that value down to 32 bits. As soon as that allocation occurs, the very next line of code, they use that same value to copy the values from user mode into kernel mode. However, the copy function uses the whole 64-bit values. So obviously what we can do is we can pass in a 64-bit value. This will get truncated, and it will cause a controllable heap overflow. Now this is very bad because what it allowed was an unprivileged local attacker to gain full code execution in the context of the kernel, which is kind of like a game over. And again, a little ironic that a security product has these security vulnerabilities. Another issue I found while working on these slides also affected Little Snitch. I wasn't really picking on Little Snitch per se, it's just it's the most popular product, so I was focusing most of my attention here. Turns out that the updater or installer for the firewall product does not validate or doesn't fully validate the components it's installing or updating. So what a local unprivileged attacker can do is modify the components, and then the firewall installer will naively and blindly install them and execute them as root without validating them. So basically what a local attacker could do is wait until the user either installed the firewall or more likely wait to update them and kind of do a local man in the middle to modify the downloaded files before the firewall went and used them. And there's a huge window of time, so this is a very easy exploit to win. So again, we modify these components, we can inject a backdoor or some script, and then again, the installer, which is running with root privileges, will blindly execute them. So again, a great effective way for a local unprivileged attacker to get root privileges. Okay, let's now talk about how to bypass firewalls. First, we'll look at ways to bypass each of the most popular third-party Mac firewalls. And then we'll talk about generic bypasses that can fully bypass all of the products. Now, I do like to clarify or make the point that for any security product, if an attacker or piece of malware is proactively targeting that, they will be able to find a way to bypass that. So in my opinion, these are not CVE-worthy flaws. Again, it's an inevitability, right? If you write a firewall product and there's a piece of malware that is trying to bypass your specific firewall product, they will succeed. Same with an antivirus product, same with any behavioral-based heuristic product. Okay, so the first one we're going to talk about is radio silence. And again, our goal is to somehow be allowed to access the network without these firewall products detecting or alerting the user that this is what we're trying to do. So radio silence is interesting because it's actually a firewall product that kind of takes a blacklist approach. That is to say, by default, it will allow any new traffic. The user has to manually go in and blacklist certain applications that they want it to block. So if we look at the disassembly, reverse engineer the kernel extension, we can look at their blacklist logic. And we can see that there is a stir compare where they're checking the name of the process. And it appears that if the name of the process is launchd, that cannot be blacklisted. So let's test this. Let's create a piece of malware and name it launchd. Again, the path doesn't matter. It can be in the temp directory, users directory, wherever. If we manually create a rule to blacklist this process, because again, this is a blacklisting-based firewall, we go ahead and create that rule and say, do not allow this process to access the network. If we then execute this malware, because it is named launchd and because the firewall is not checking the full path and validating any code signing information, it's just checking the name, since we are called launchd, it will say, okay, this is something that cannot be blacklisted, so I will allow it out. So again, a very trivial way to fully bypass radio silence. Another popular Mac firewall product is hands-off. Turns out we can bypass this product by sending a synthetic event to the alert window. So say we want to execute curl. Curl is a built-in utility on macOS that a lot of malware or attackers will use to download either second-stage implants or data from the web. We can see that, as expected, the firewall sees this outgoing connection and generates an alert. What a local attacker can do, though, is send a programmatic or synthetic click to the OK button, which basically will tell the firewall to allow the event. The firewall isn't doing any detection of such an event, so it basically just assumes that the user is the one clicking allow. Of course, it's our malicious code. And of course, there's also ways to do this invisibly. We can wait till the user is not active, we can dim the screen or wait till the display is asleep. So even though we are interacting with a UI component, we can do this fully invisibly. Next on, we have Lulu. Lulu is the open source firewall I wrote. And since its source code is open source, it's pretty easy to understand how it's going, how it works, so it means it's also easy in some scenarios to find a bypass. So by default, Lulu trusts Apple binaries, system binaries, etc., etc. This is a preference, but it's on by default. However, it has a concept of a gray list. And a gray list is a list of binaries that an attacker could potentially use to perform unauthorized network activities. For example, curl, netcat, etc. These are, yes, signed by Apple, but if someone's executing netcat, the firewall should still alert the user and tell them what's going on. So the question is, as an attacker, can we find another system utility that's signed by Apple that is not on this gray list? And the answer was yes. Turns out we can use the whois utility to exfiltrate data. If we look at the debug log from the firewall, we can see that when whois is executed, the firewall sees the network traffic, because again, it's running in the kernel, so it's going to see all network traffic. However, since whois is signed by Apple proper and is not on the gray list, the firewall says, okay, this is a trusted Apple application, I'm going to let it out. So it does. And then finally we have Little Snitch. Little Snitch is the de facto, the most popular firewall for macOS. If we look at its rules, we can see it has an undeletable system rule that says anybody, any process, any application can talk to Apple's servers, specifically iCloud.com. So to test this, we can manually create a rule to block curl or netcat. And then if we connect to Apple servers, for example, if we connect to iCloud, we can see that this connection is still allowed even though we've explicitly told the firewall to block curl. So a while back, I reverse engineered the iCloud protocol and I set up a command and control server on iDrive. Now, once we have this command and control server on iDrive, which is hosted in iCloud, we can then write malware that once it gets on a system, even if that system has Little Snitch installed, it can exfiltrate any data it wants to this command and control server. Again, the firewall will see this connection because it sees all network connections, but because it has this undeletable system rule that says anybody can talk to iCloud, it will allow the connection to go through. So again, a trivial way to bypass Little Snitch. Okay, so those were product-specific bypasses. And in some ways, they're kind of cool, they're kind of neat, but in another way, they're also kind of lame. And the reason they're kind of lame is, in practical, if you're a real attacker or a real piece of malware, there's a lot of steps you have to perform, right? First, you have to detect that a firewall is installed. Then you have to detect what specific firewall. Is it Little Snitch? Is it Lulu? Is it Radio Silence? If it's hands-off. And then you have to utilize that product-specific bypass, which means you have to implement code for each of those attacks. So that gets unwieldy, that gets kind of complex. So let's now talk about generic bypasses, which in my opinion are much, much better, way more powerful. And what I mean by a generic bypass is a bypass, a way for an attacker to access the network, regardless of what firewall product is installed. Now, these are all possible because firewalls must allow certain network traffic. For example, they have to let system protocols talk to the network, perhaps libraries and system updaters. Also, the user is going to invariably allow certain applications to access the network. I mean, think about your bank, right? There's a lot of applications that you use that would be completely useless if they were not allowed to access the network, for example, the browser. So what we do to find or exploit these generic bypasses are two steps. So first, we're going to passively sniff or observe what network traffic is allowed. So imagine, again, you're an attacker or a piece of malware. You gain code execution on a Mac system. The first step, again, is to just quietly, passively watch for a few hours, a few days, and kind of map out or understand, again, fully passively, what network traffic is allowed out. And then what we can do is talk about abusing those protocols or processes to generically bypass any firewalls. So as I mentioned, the first thing we want to do is figure out on any system what network traffic is allowed. If there's no firewall installed, if there's a firewall, what rules does it let through, what applications, what processes, what protocols. And we can do this without any special privileges using the LSOF utility that's baked in or built into macOS. So if we execute this on my box, it's a little hard to read, but we can see there's a variety of applications, none too surprisingly, that are allowed to access the network. We have things like my browser, Chrome, Safari. We have things like chat applications. We have other apps like Adobe, VMware. I mean, really just think about all the apps and processes you use on your system that are allowed to access the network, even if you have a firewall installed. Via LSOF, we can passively determine what those are. And yes, some of these applications may have endpoint-specific rules. For example, the firewall might say only allow Adobe to talk to Adobe's servers, or only allow Slack to talk to Slack servers. But good for the attacker is most of these services are talking to cloud-based endpoints. So if we actually look at the IP addresses or where they resolve, the majority of them are in AWS. So it's very easy for us as an attacker to set up, for example, a command and control server similarly on AWS. Okay, so now we have a good understanding of what traffic and what processes are allowed through the firewall and to talk to the network. So let's now talk about exploiting these to generically bypass any third-party Mac firewall. So the first generic bypass we're going to use indirectly exploits the trust of a process via a trusted protocol. So on macOS, it turns out that DNS requests are handled by Apple's MDNS responder daemon. So this means if any application on the system, whether that's your browser or a piece of malware, if it makes a DNS request to resolve an IP address or a URL, this will actually be handled by a trusted system daemon. So basically, locally, an XPC message is sent to the trusted system daemon, and then that daemon is what makes the actual DNS request to resolve the name. So the firewall will see this request because, again, it's monitoring all network traffic, but it's going to have to allow it through because it's coming from the trusted DNS daemon that is handling all DNS requests for the entire system. So malware can easily abuse this fact to very simply build a fully bidirectional command and control channel via DNS. Again, as the network requests originated from the trusted process context of the system DNS daemon, the firewall will have no choice but to allow it. DNS command and control is well understood, so we won't talk about how to build such a protocol, but suffice to say, it's pretty easy to build one that will allow you in DNS requests to both exfiltrate data and also gain tasking from a remote server. Next up, let's talk about abusing browsers, because the simple fact is if an infected system has a browser and the user is using that browser, it will be given indiscriminate network access, or at least full network access to any remote web server, HTTP or HTTPS. And again, we can passively determine this. We can watch the user for a few hours, a few days to confirm, okay, yes, they're, for example, using Google Chrome, and Google Chrome is able to talk to these hundreds of thousands of sites. So again, the firewall is going to trust the user's browser. So let's abuse this fact to generate network traffic from the process context of the browser that the firewall will have no choice but to allow. So the first way we can do this is via Apple scripts. As we can see on the slide, we're going to kindly ask Safari to browse invisibly to an attacker-controlled command and control server, and we can send any data we'd like to exfiltrate as a data parameter. So again, very simple, a few lines of Apple script. We're basically telling Safari, please browse to this URL. And again, since we set the flag to invisible, the user won't observe this. Now again, the firewall will see this request because it sees everything, but it's coming from the user's browser, which via LSOF we've determined is allowed to access the network. So the firewall is going to say, yeah, this is just a network request from the browser. I'm going to let it through without alerting the user. An even better way to generically bypass firewalls is to abuse browsers' command line interfaces. It really doesn't get easier than this. Again, very easy to determine what the user's default browser is, and via LSOF see what it is, and confirm that yes, it's allowed to talk to any remote network server endpoint. And then what we can do is all modern browsers now support a command line interface, so you can just execute that from the terminal and specify the URL you want to browse. And again, using parameter encoding, you can specify any data you would like to exfiltrate. For example, the user's passwords, text messages, whatever data you want to exfiltrate off the system. The response will also come back, and you will be able to process that. So you can see what the remote command and control server has as well, which provides a means to specify tasking to the network. Again, the firewall will see this network traffic, but because it's coming from the trusted context of the browser, it will let it through. No questions asked.
Very good.
Another way to abuse, or another technique to abuse any program that's trusted to bypass firewalls generically is to inject code into that process. Again, firewalls are going to trust specific programs, browser, chat application, whatever. And so if you can inject code into those processes and then generate a network request from that, the firewall will see that, but because it's coming from within the trusted process context, it will be allowed. So there's a variety of ways to do process injection on macOS, and we'll talk about some of them briefly here. So first up is traditional injection. Now, generally, Apple will block this if you're trying to inject into an Apple-specific process. But if you're trying to inject into a third-party application, this generally still works. So again, we can determine what third-party applications are allowed to talk to the network. For example, I have Slack installed on my system, and I've told my firewall, yes, Slack is allowed to talk to the internet. So what an attacker could do is they could determine that, and then they could inject code into Slack and gain access to the network. So what we do is we first remotely allocate memory in the Slack's address space, and then we just copy in some shellcode, load a dynamic library, and then execute our network requests from there. Again, the firewall will see this request, but since it's coming from a trusted allowed process, it will be allowed. Another method to inject a dynamic library at load time is to use environment variables. So you can use the DYLD insert libraries environment variables, and this tells the operating system to, at load time, please execute whatever dilib you specify in the process context of the application you specify. So again, here we target Slack, and we basically give it the path to our malicious dilib. Again, this dynamic library is the one that's going to do the network command and control that the firewall would normally detect. But since it is loaded into the process context of Slack, which on my system is trusted, once the dynamic library gets loaded, if we have a custom constructor, this will be executed. And again, this will be executed within Slack, so the firewall will allow it because the network request is coming from within the Slack application. Next up, another kind of injection technique is something I like to call dilib proxying, which conceptually is fairly simple. What you do is you target an application that's allowed to access the network, and you find a dynamic library or a framework that it's linked against, and you just replace that with a malicious one. So for third-party applications, the operating system will not validate that that's not been tampered with, so we'll naively and blindly load your malicious dilib in place of the original one that you overwrote, And again, once you're then in the process space, you can connect out without worrying about a firewall alert. So to perform this proxying, what you do is you first make a copy of the original dynamic library. And then what you do is you save your malicious dilib with the same name of the original dynamic library. And what you do is you also then forward or proxy all symbols and exported methods, functions to the original dilib, because you don't want to break legitimate functionality. Right? Woo! Does this mean I'm talking too much? I'm almost done. Thank you. That was, all right, now I'm awake. All right, so where were we? Okay, yes. So if you blindly just replace a dynamic library that an application is linked, and you don't forward the symbols or the methods that the application expects, when the application or the loader tries to load the application, this is just going to crash. So what we do is we basically tell the loader, and you can do this with various linker directives, that any requests in this malicious library for the symbols and methods should be proxied to the original dilib, and you can again specify that path. So if you do this, everything works seamlessly, transparently. This is actually a very, very powerful technique that I'm really surprised more malware doesn't use, because not only is it a great way to gain persistence, it's also a very stealthy way to gain code execution in third-party applications, which then allow you to do things like access the network. Now, the final way to bypass generically any third-party firewall product is to get code execution in the kernel. In short, if an attacker can load a kernel extension or find a way to execute code in the context of the kernel, they will have no problem bypassing any firewall. First, those firewalls generically allow any code or any network connections that originate from the kernel. So for example, if we look at the source code for Lulu, we can see that it fully trusts kernel sockets. And this is because it assumes, as do all other firewall products, that if something is executing from the kernel, it's probably something from the system, so that should not be blocked. Because if you're blocking kernel sockets, potentially you can break all sorts of legitimate functionality of the operating system. Also, if you're in the kernel, you can do more subversive things like actually unhook or unregister any installed firewall. So at the beginning, we talked about these socket filters, and we talked about how you register them. When you register them, that basically adds your socket filter to a linked list or some other kernel structure. There's nothing to say that an attacker's kernel level code doesn't go through those structures and basically unregisters them. So again, this will transparently disable the firewall and then allow any attacker code to connect to the network without alerting the user. Now, a valid question is, how do we get code running in the kernel? On recent versions of macOS, kernel extensions have to be signed. So a really good way to bypass this code signing requirement is simply bring a buggy, albeit signed third-party driver to your target, load that kernel extension, the operating system will allow it because it's signed, and then you locally exploit that to gain code execution in the context of the kernel. Interestingly, the Slingshot ADT did exactly this on Windows to bypass Microsoft's kernel code signing enforcement. So I talked about this attack at DEF CON a few years ago, specifically showing how we could use the buggy little snitch kernel extension, which we talked about, the exploitable heap overflow. Again, you would just bring that kernel extension with you to a target, load that, the operating system would allow it because it's validly signed, and then you exploit the vulnerability to gain code execution in the kernel. Since then, Apple has added something called user-approved kernel extension loading. Basically, they say, okay, this kernel extension is signed, but we want the user to manually approve that so that it blocks exactly this kind of attack. Turns out the way they implement that had a flaw, and you could send a synthetic click to it. I reported this to Apple, and they fixed it, and at the time they believed that everything was fixed. But it turned out that they had another flaw in their implementation. So they tried to protect the button that asks the user to allow the kernel extension, because if there was a way for us to programmatically interface with that button as a local piece of malware, we could just send a synthetic mouse click and click allow, basically masquerading as the user, which would completely make that alert worthless. So it turned out, even though Apple patched the original attack vector, there was another flaw in the way they handled synthetic events. So what you could do is you could actually send a mouse down event, and then send another mouse down event to this button. And for some unknown reason, when the operating system saw that second mouse down event, it would translate it to a mouse up event. This button, which was filtering for synthetic events, would see that the mouse up event was coming from the kernel, and thus would allow it. So all you had to do to bypass this Apple-touted foundational security mechanism was send 2 mouse down events. Apple gets a lot of grief for their security posture, or they should, and I think this is a great example of, it's really not that hard to bypass a lot of their security mechanisms, regardless of what you or their marketing team tells you. All right, so let's wrap this all up. So today we talked first about building a firewall for macOS. We showed that using socket filters, you could very easily build a very powerful kernel extension in the firewall for macOS. And we brought this all together with Lulu. Lulu is a full, comprehensive, free open source firewall for macOS. So if you're interested in kind of more of the details or writing your own, or perhaps extending the product, check out the source code on GitHub. It's all forwarded. We then kind of changed gears and talked about how to bypass these products. Turns out that firewalls are complex pieces of software, so a lot of times have exploitable security bugs, so audit away. And we also showed that the sad reality is that even though no public Mac malware is utilizing these techniques today, it's actually very, very easy to generically bypass any third-party Mac security product. Now, I just want to end by noting that this doesn't mean that firewalls are useless, but it really makes a case for a defense-in-depth strategy. And I fell into this mentality myself where I said, okay, AV products are kind of crap. All I need is a firewall product. Well, this research really showed that that was not the case. It's really a good idea to have other security products. For example, perhaps you have something that's running off the box, that's monitoring your network, that is able to understand, for example, the DNS protocol and detect that a user's box at 2 a.m. is sending odd-looking DNS requests. Right? This isn't something a firewall is ever going to or should ever understand. But, we should have other security software in place that can detect this kind of attack. And finally, since you're here listening to my Mac security talk, I am assuming you're interested in Mac security. Just briefly want to mention that this November will be a brand new Mac security conference in Hawaii. We have a lineup of awesome speakers. So again, if you're interested in Mac security, iOS, check it out. It's called Objective by the Sea. All right, so that's a wrap. I really want to thank you for attending, and briefly also want to thank the Friends of Objective-C, Digital Security and Malwarebytes. And apparently, attendees of this conference are shy asking questions. I did not know that. But I will be around for the rest of the conference. So if you're interested in chatting more about Mac malware, Mac security, Mac 0 days, or bypassing Mac firewalls, I would love to chat. So again, thank you so much. Also thanks to Jay and everyone else at ROOTCON, awesome conference, and I'm super stoked to be here talking. So thank you again for your time.